The quantum weirdness powering the universe. Imagine the coldest temperature possible, absolute zero, at minus 273.15 degrees Celsius. At that point, particles should stop moving entirely. Yet quantum mechanics says you can never quite reach it. Every particle retains a minimum zero-point energy it can never shed. That same rule applies to empty space itself. What we call the vacuum isn't truly empty. It's filled with constant, fleeting ripples of energy called vacuum fluctuations. Scientists proved this with a beautifully simple experiment. Place two perfectly smooth metal plates extremely close together inside a vacuum chamber. They attract each other, with no magnets, no charges, nothing classical pushing them. The reason? Between the plates, vacuum fluctuations are restricted to only certain wavelengths, like a guitar string that can only vibrate at specific notes. Outside the plates, every possible wavelength is allowed. The result? Lower energy density between the plates than outside. That region effectively has negative energy relative to normal vacuum. At separations around 10 nanometers, the force becomes strong enough to equal 1 atmosphere of pressure. This is the famous Casimir effect, and 2025 reviews, plus fresh experiments, continue to map it in exquisite detail, even showing ways to flip the force from attraction to repulsion using clever materials and light. Negative energy isn't just a lab curiosity. It behaves in astonishing ways. In theory, regions of negative energy density could let us warp space-time itself. Picture a warp bubble. Space contracts in front of a spacecraft and expands behind it. The ship never moves faster than light locally, yet it could cross vast distances in far less time than light would take. Researchers like former NASA physicist Sonny White have even explored how tiny Casimir cavities might one day seed nanoscale versions of such bubbles. The same exotic ingredient could hold open a traversable wormhole, a shortcut through space-time. Recent 2025 theoretical work has proposed Casimir-inspired designs that naturally produce the required negative energy densities. The catch? The amounts needed for anything macroscopic are enormous compared with what we can currently generate. Stability and quantum effects remain huge hurdles. Negative energy also explains how black holes can slowly disappear. Near the event horizon, virtual particle pairs constantly pop into existence. If one falls in while the other escapes, the infalling particle carries negative energy, reducing the black hole's mass. Over immense timescales, this Hawking radiation causes even the largest black holes to evaporate completely. Direct observation in real black holes is still pending, but laboratory analogs, using Bose-Einstein condensates, fluids, and optical systems, have now repeatedly produced Hawking-like radiation, complete with quantum entanglement signatures. Analyses of LIGO gravitational wave data from black hole mergers have even turned up tantalizing hints of possible echoes consistent with stimulated Hawking radiation. The theory that first united quantum mechanics with general relativity continues to gain experimental support, even if the final smoking gun for astrophysical black holes remains elusive. In 2026, the story gets even more exciting. A startup called Casimir just raised $12 million to commercialize chips that harvest usable energy directly from quantum vacuum fluctuations, turning the Casimir effect from a demonstration into a potential power source. From the tiniest plates in a lab to the hearts of black holes and the dream of interstellar travel, negative energy reveals a universe far stranger and more interconnected than we once imagined. The vacuum isn't empty. It's alive with possibility. And the best part? We're only just beginning to listen to what it has to say.